All right, so we're going to talk about the polar form of complex numbers. So lecture 32 of Specialist Maths. Again, some of the prior knowledge for this will be Introduction to Complex Numbers and the most recent video, which was the modulus, the conjugate, as well as division of complex numbers. For this video in particular, it'll be helpful that if you've seen a video on circular functions, which was actually the first video in this whole series. So I'll put links below for all of them. What we're going to cover in this video is the definition of complex numbers in polar form, Argand diagrams in polar form, what's called the non-uniqueness of polar form, the principal value of the argument, and the complex conjugate in polar form. So you're probably wondering, what on earth is polar form? It's just another way we can represent complex numbers, and it's useful because it sometimes simplifies problems that we're doing. So let's jump ahead and look at the definition of the complex number in polar form. Here it is. If you want to define a complex number, a plus bi in polar form, you're going to know from previous videos that that is some point in space. And remember, a represents the real component. So that's sort of the space it occupies on the real axis. And then b is the imaginary component. So you end up with a complex number a plus bi. If we call this r, sort of representing radius, if you think about a bit of circular functions work that you've done by now, think about this as r, and then what you can do is, we can say that this length here, b, which is just the imaginary component's height, or this length here, I think you would agree, just using some SOHCAHTOA, that must be equal to r multiplied by sine theta. And similarly, this length here, a, must be r multiplied by cosine theta. So we end up just with this triangle here. And then so what we do is we sub that into for a and b. So we get r cosine theta plus r sine theta multiplied by I, just subbing in a and b as their respective things. You notice r is a common factor, so take that out the front. So you're left with r cosine of theta plus I sine theta. Okay, and then we just shorten this and we say r cis theta, where cis theta is this operation that represents cosine theta plus I sine theta. That's just a nightmare to write that all the time, so we just shorten it to CIS, cos plus I sine. Okay, and we know that r, just pointing out as well, that the magnitude of r, or the length of this blue line, is the square root of a squared plus b squared. Okay? And theta, I think you would agree, is the tan inverse of b over a. So, yeah, tan is opposite over adjacent. So if we take b divided by a, then that is that angle in there. Okay, so just some sort of additional things you might need to know, because now you know what r is and theta is, you can sort of compute that. If you use these key ideas here, you can see how they're important for understanding the polar form. Polar form, I should mention, is also sometimes known as the modulus argument form. So important to be aware of that in case you see it written differently. I think mostly we talk about it as polar form though. Okay, let's chat about the next thing, which is Argand diagrams in polar form. All right, so yeah, just recalling that our Argand diagram has the real axis and the imaginary axes. A polar Argand diagram uses rays at pi on 2 radians. So you can see here, it's quite new, but you've got this new way of sort of representing our complex numbers on this polar Argand diagram. And basically each ray here represents pi on 12 radian increments. So pi on 12, pi on 6, pi on 4, pi on 3, whatever this one is, and then pi on 2. And so we're going around in increments of pi on 12. I suppose the other thing to point out is each circle here represents a radius of 1. So you notice this circle here has a radius of 1, this circle here has a radius of 2. So you can see how useful that might be for representing our complex numbers in polar form, because we know that the number at the front is basically the length from the origin to the point. And then now we know that we use the angle, so we can sort of tell what angle it's on by using these increments of pi on 12 radians. So it's a pretty helpful way to sort of visualize things, and this is what's called our polar grid. So let's just look at one example of polar form. So for example, if you had 1 plus the square root of 3i, so that's it in sort of Cartesian form, the original form, what we could do is we could think to ourselves, okay, what point has the coordinate with sorry, one sec. Sorry, I should have put more explanation here in terms of how we get from here to here. But this 2, remember, is the radius. So we can see that this 2 has not come out of nowhere. It's the square root of the square root of 3 squared, which is 3, plus the square root of 1 squared, which is 1. So it's the square root of 4, which is 2. So this 2 and this 2, for that matter, have come from, from over here, right? From taking the modulus of z, the length of that blue line from the origin to the complex number. And similarly, this pi on 3 has come from here, tan inverse of opposite over adjacent. So tan inverse of root 3, because it's root 3 divided by 1, which is just root 3. Tan inverse of root 3 is pi on 3. So we end up with 2 cos of pi on 3 plus I sine of pi on 3, okay, which we shorten to 2 cis pi on 3. Okay, and so that's this example here, that's this point, and here's just another example. 3 cis negative pi on 4, and that should make sense because you can see that it's a radius of 3 away, 1, 2, 3, and we've gone negative pi on 4, which is negative 45 degrees. So we're down here, roughly. Well, not roughly, exactly, we're at that point. I encourage you as a little exercise, see if you can convert that back to Cartesian form and see how you go with that. Okay, let's keep moving. So the next thing we want to talk about is what's called the non-uniqueness of polar form. So we say that a complex number can have multiple representations in polar form, and you'll see why. And the reason is because cosine and sine are periodic. Again, you've hopefully learned a little bit about circular functions, which basically means they start to repeat after 2 pi. So cosine of theta is also equal to cosine of theta plus even multiples of pi. And similarly for sine, okay, where z is some integer, right? Or sorry, n is some integer. So any number you put here, you're going to get an even number. So any even multiples of pi, you're just going to repeat. I sound like I'm repeating myself, so let me just get to the point. You can see if we rotate this by 2 pi radians, we get back to where we started, right? So you can sort of see why if we added 2 pi to pi on 3, we would be back at the same point in our grid. So that's a relevant fact. And so obviously with our polar form, when we combine these, r of cis theta is equal to r of cis theta plus 2n pi for the same reasons, because we're just combining them. Okay, by convention, we say we choose that theta is between negative pi and pi. So remember, negative pi is negative pi is negative 180 degrees. Pi is positive 180 degrees. So we sort of just picking values for what's called, we choose values of theta between negative pi and pi. Because we could choose values outside that, but that's just a convention that we pick values in between negative pi and pi. Okay, and essentially that's what's called the principal argument. So for a non-zero complex number z, the argument of z that belongs to the interval negative pi to pi is called the principal argument of z and is denoted arg of z. That is, the argument of z is always between negative pi and positive pi. Not including negative pi, but including positive pi. Yeah, sorry, I should just remind us, the argument of z is referring to this. So let's go back here. So you notice here it's got lowercase a. So that's the argument of z, lowercase argument. And so the principal argument is when you take this thing in here to be between negative pi and positive pi. Otherwise, we use a lowercase a for the argument. Okay, remember the argument refers to what's in the bracket, so it's basically referring to the angle. So the principal argument has to be between negative pi and pi. The argument, lowercase a, can be any angle though. Okay, let's have a look at the last thing, which is the complex conjugate in polar form. So this is pretty straightforward, I hope. The complex conjugate z bar is obtained by reflecting the point z across the real axis. So same as before, if you've got some complex number here, now in polar form, 2 cis pi on 3. We've seen in Cartesian form, it's the same. If you want to find the complex conjugate, you're reflecting across the real axis. So essentially, you are down here now. So the complex conjugate z bar is 2 cis negative pi on 3. So you just do the same thing, but you make the angle negative, and then that finds the complex conjugate in polar form. So hopefully that's straightforward. But remember, that's useful because what we're going to start to talk about soon is things like operations on complex numbers, which we've done in Cartesian form, but now we're going to start doing them in polar form. And so if you recall, we needed the complex conjugate to do division in Cartesian form, and similarly we'll need the complex conjugate in polar form to be able to do division in polar form. So hopefully that's making some sense. If you're finding these videos at all helpful, give us a thumbs up, like and subscribe, all of that fun stuff. And I'll talk to you soon. Good luck with all your studies.